We are here for another day of Unit 7. So we are going to start like we always do, and we're going to roll that information forward in a warm-up that's going to be related to stuff we have already covered. Then we're going to move through to a Kahoot today, and then we're going to finish by coming back together and doing some assignments. If you could turn your cameras on, it would make me feel better because I've been talking to black screens all day. If you feel comfortable, it makes me happy to see your faces. So things you need to have in your hands, okay, right now. 1, you need your Unit 7 notes. You will not be able to do the Kahoot without your Unit 7 notes. So I would get those out now before we start, okay? 2, you need your reference packet. You always need your reference packet, but I'm just gonna say it again. Please have your reference packet. I'll be getting information to you as necessary through the reference packet, and I'll actually have it pulled up and be going back and forth during our lesson today. We're also going to be doing a Kahoot, so whatever you use to do Kahoot at home, whether you have it on your phone while you're looking at the screen or whatever it is, you need to have that open. And then you're going to want scratch paper or notes or your notebook or whatever else while we go through these examples, okay? So as a reminder, QC 7.1 was already due. But if you emailed me for an extension, you must attend tutoring the day you asked to attend tutoring. I put notes in Skyward. I'm not all the way through 6th period, but I put notes in Skyward next to QC 7.1. I marked it as missing, but said extension without penalty to this date based on your email. I'm going to start doing that to track for your parents and for me. So it's not, doesn't look willy-nilly because it's not, it's very intentional. So you must attend tutoring or the extension is canceled. Okay, so if you told me you were going to come to tutoring or email me that you're going to come tomorrow morning. Okay, because I already have notes of who should be there. If you did not score well on 7.1, that is what we're going over in tutoring today. So I highly recommend coming to tutoring. If after we do this question, it doesn't make more sense, please come to tutoring today or tomorrow morning. Okay. Are there any questions about anything we've covered so far, due dates, whatever, before we start? Covering all our bases. Now the internet's been real spotty here. So if my voice starts lagging or looking robot or sounding robotic or whatever, please tell me in the chat sooner rather than later. I have the chat pulled up because I was talking like a robot last class and I didn't know it. And I had to like reset some stuff. So let me know if I sound awful or weird. I have the chat up. Okay. Alrighty, getting started with this first question. Now, this first question we've spent our time on, we've taken our time on because this is reviewing concepts all the way from last semester through right now. So I'm going to use the wheel to pick on wonderful peoples to help me with this assignment. So first up, Jimin, what do I have to do for this question before I do anything else? What's the first thing we do with any question we're given?
Identify what we have to get.
Yes, we have to identify what we're looking for, right? So in this question, it says, what mass of iron can be produced if 6.521 grams of zinc are added to iron 3 chloride solution? So tell me, Jim, what do you think this question is asking for?
Mass of iron.
It's looking for the mass of iron. And when we're done, what will that mass of iron look like? What unit is it?
Grams.
And then what's the chemical symbol for iron?
Fe.
Yes, it's based on a Latin word called ferrous. So Fe, it's weird. It doesn't look like iron, but I swear it means the same. Good job, Jimin. All right, next up on the chopping block, the question block. Ray, what do I do now? Ray, oh, I see you're here. Awesome. Ray, Bobe, banana, fin.
Hello?
Hello. I heard and then nothing.
Oh, you set up a formula? I don't know.
Yeah, you set up the chemical formula, right? So when we say what mass of iron can be produced, when I see this word, this screams chemical reaction, right? That's how we know this is stoichiometry, not just dimensional analysis. Remember, stoichiometry is a weird German word for dimensional analysis with a chemical reaction. We're just relating things, right? Mm-hmm. So the words can be produced means we have a chemical reaction. So let's build it, because for every single question, we need to have the reaction and it needs to be balanced. Awesome. So help me start building this. What are some important pieces of information? Screen.
So the given is 6.521 grams of zinc,
Okay,
and
so
then we're trying to
go ahead. 6.21 grams of zinc. What is the chemical formula for zinc?
oh god, can I pull up? I'm gonna pull up
Absolutely,
teacher.
you can pull up. Go ahead, pull up, look up, whatever you need. I was about to write it and I was like, nah, I'm not going to make it easy on you guys. You're really good.
Um,
What's the chemical symbol for zinc?
oh, chemicals. ZN. I didn't. Yeah.
Yeah, you're
My
good.
bad. That's on me. I was like,
521 grams of zinc is our known. Okay, so how does that fit into our equation? So it says
would it be on the top of the first like fraction?
okay, so right now what you're talking about is setting up what, oh, that's really not straight, is setting up a railroad track. But before we set up our railroad track, so we know step one, we're going to be doing
Mhm.
something. One of those steps is comparing moles, right? Can we compare moles right now? Do we have the information we need?
Um, yes. So we convert to moles, and then it would be like, would it be 6.512 grams of zinc over 1?
So that is how much we are given.
Oh wait, oh, is it over Avogadro's number?
Nope, nope. You are laser focused on the fraction. I want you to zoom back. So remember when we did the drag and drop? Do you remember when we did the drag and drop activity with the slides? What did I give you every time that you used every time? What did I give you before you started the problem?
The reference packet.
The reference packet, yes, but on those Google slides, like on the physical Google slides.
Was it grams to
Hold
the
on.
amount of? Oh,
Here we go. I'm going to go here. I'm going to pull it up for you so you can see.
okay.
Talking about these. Remember when we did this?
Oh yeah.
What did I give you every time?
Oh, you gave us the the chemical equation.
Yeah, the chemical equation or chemical reaction. Do you have one here?
We don't have one yet.
We don't have one yet, but we will, right? Because you guys are awesome. So that was my whole point there. I was being real ski. I know, like I was being a little weird, but the whole point is we can't do anything without the chemical reaction. You used it every time. So if I don't give it to you, you have to make it. And that was the hardest part of 7.1. All of you killed that Google Slides activity if I gave you the reaction. As soon as I take it away, that's where we get the weird butterflies in our stomach and things feel weird and awful, right? And that feeling is learning and uncertainty, and it's beautiful, and you should embrace it. If you've never felt those butterflies looking at a problem, you have never challenged yourself, and that's a sad way to live. Okay, so we are going to create the reaction. And Ray, you did a great job, but I took you down this weird, like Alice in Wonderland rabbit hole. So I'll pick on someone else now, but you did great, right? Okay.
Okay. Yeah. I was like confused like halfway through because I didn't know what we were like trying to do, and then I was like, oh, okay, that makes sense. Yeah.
I had a destination and you weren't sure what it was, and it felt a little awful. I know. And I picked on you for a long time, but it's good. Guess what? That has happened every single class today. Everyone started the railroad tracks, and a couple of classes I let them go forward and then they got stuck. But then what happened was, since we went back and forth, people got confused on what they should do first, and I ended up having to reteach the whole thing. So
Oh, okay.
I stopped you because of what I learned from prior classes. So thank third period in a very long class that felt kind of awkward at first. And now I have a better process. Okay. So
Okay.
yes, I stopped you so we could do the chemical reaction. And I'll pick on someone else to do that. You did a great job, I promise. Okay. Kai, how do I start with this chemical reaction?
You have to look at like what the products are and then like what the reactants are.
Awesome. So let's put that arrow. Reactants go on the left or the right?
The left.
Reactants on the left, products on the right. So let's start filling them in. What do I know?
You know that you're producing iron.
Yes, and that iron is not a compound. So we already said Fe was the chemical symbol. The next big question is what phase state is that? Remember, we have the options of solid, liquid, gas, or aqueous, right? What
Mhm.
phase is iron going to be, do you think?
I think it's solid.
It is solid. Your spidey
Okay.
senses are correct. Why did you say solid?
I don't know. I just guessed because it's like a metal
Yes,
inside.
it's a metal. Yeah, no, that's exactly it. That isn't a guess.
Okay,
It
yay.
was an educated estimation based on prior knowledge. So you weren't guessing. Guessing is I have no clue and I'm saying something random. You had a very specific reason why you thought that, and that reason was correct. So you did a great job. Okay. Iron is solid. What is the only metal that's liquid at room temperature? Does anyone know? The only metal liquid at room temperature.
Is it mercury?
It is mercury. Like, you guys are way too young. They already outlawed mercury thermometers by the time y'all were born, but like we used to play with them. That's probably why we're all a little off. But like we used to play with mercury thermometers, like break them and play with it was so fun. Like I'm telling you, it was not safe. Like if you had gloves and like a mask on, it would be super fun to do, but I wouldn't recommend it if you don't have a mask because mercury poisoning is no joke. All right. So we have an iron solid and we know that's going to be a reactant, right? So what else do we know? Here, I'm going to pick on someone else now. You did a great job, Kai. What else do we know? Celine, what else do we know?
We need to go from grams to mass.
We need to go from grams to mass, but we're still building the chemical reaction right now. We're going to stick with this chemical reaction for a minute, okay? So we know one product is iron. We use this piece of information. So that piece of information is gone. We did this, we've used it. And we use the can be produced to tell it was on the product size. What else do we know? What else can we cross off?
Iron 3 chloride.
Iron 3 chloride, is that a reactant or a product?
Product.
So it says, let's read it again.
Well, it's on the left side.
Yeah, it's on the left,
So
which is a
reactant.
yes, because it says the grams of zinc are added to iron 3 chloride. So this right here, this section, are added to means that I am taking zinc and mixing it with this and seeing what happens. Okay, so that are added to tells me it's a reactant. Everything on both sides. So this and this have to be a reactant because they're added together. If you say was produced, was made, was the result of, that's when we know it's a product. Okay, so those English keywords. So we know zinc, you said iron 3 chloride, right? So how do we build iron 3 chloride as a compound? What do I write? You remember how to do it? I'm actually going to erase this. I'm going to bring this back later. Okay.
FeCl3.
How did you get there? Because that is perfectly correct. And if someone didn't know how, I want to make sure they know. Ah, stop it, Marker. Are you there? I'm sorry, I'm not hearing you.
You were frozen.
Oh, sorry. How did you get to iron 3 chloride? See, my internet's funky.
Well, the 3 Roman numerals corresponds. And then iron is first.
Yeah, so what she's talking about, if you weren't aware, we were using this last class. Hold on. Go back. This right here. So iron has multiple oxidation states, and the Roman numeral 3 is showing me that it is +3, okay? Not the other. So iron is 3 plus. So that's what she was referring to. So that's iron 3 plus. Chlorine is always 1 minus, and that is also on that chart. You have to make them balance to 0. Right now we have 3 plus and 1 minus. That adds to 2 plus. That is not what we wanted. Add another one, that gets me to 1 plus. Another one, that gets me to 0, which is what I wanted. So I need 1 iron, which is why there's only 1 here. I need 1, 2, 3 chlorines, which is why there's 3 here. Last question for you, Celine. What phase state is this? What state?
Solid.
So it says iron 3 chloride solution. What does the word solution
Oh,
always
aqueous.
aqueous, right? It means that it is dissolved in water. Awesome. You did a great job. Thank you, Levy. Next person. Sneha, you're up. What else do I know?
We also know that there's the zinc.
Yes, where does the zinc go, on the left or the right?
The zinc goes on the left.
Yes, because it is attached to the words are added to. So that means that zinc is added to iron 3 chloride and we see what happens, right? So zinc, we already said was Zn. What phase is zinc?
It's a solid.
It's a solid, right? So zinc is a solid. I put that plus on the wrong side. I'm going to erase it. Okay, so we know zinc is a solid. Now, is our reaction done?
No.
Why not?
Because you need more products.
Because I need more products. Why do I know I need more products if someone's lost or confused? How did you know that?
Because it's a single replacement, so there's not like all the elements on both sides.
You're doing so well that you're having a hard time break it back. So we have that curse of knowledge thing going on that we don't remember how to not remember. So what I was asking is how you know it's single replacement and how you know those things. And most of that's because there's zinc on one side, but not on the other, right? So we must not be done. And you knew it was single replacement because for single replacement, we have 1, 2, 3 different atoms. So when we have 3 atoms, 1 in a pair, 1 not, we know that is a single replacement reaction. So how do we reform the other product in a single replacement reaction? What do we do?
I'm not sure.
Okay, so let's walk it through. So we know we have zinc and iron and chloride, okay? Iron ends up by itself. So who did iron break up with?
It was chlorine.
It was chlorine, and we know iron's now by itself. So who is chlorine's new partner?
Zinc.
Yeah, because we already used this one. So we know it must be zinc that's partnered with chlorine or chloride. And what do we have to do now?
We have to put a subscript 2.
Yes, so we know we have zinc chloride, right? What charge is zinc? What oxidation number is the only oxidation number possible?
2.
It is 2 plus, and then chlorine.
Chlorine is 1 minus.
So what chemical formula do I need? I have a 2 plus and a 1 minus. How do I get them to add a 0?
CnCl2.
Yep, because we need 2 chlorines to combat the 1, 2 positive. So it's CnCl2. And last thing, what phase state is this? How do you tell?
It would be aqueous, I think.
Yes, it is aqueous, but how can you know instead of think?
The solubility rules on the reference pack.
Yeah, so you go to the solubility rules. Dun, 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 dun. We're going to do this. Let's see. 1, 2, 3. Okay. Wait. Here. Yep. So you see, let me erase all these because we were using these for the Kahoot. Okay. So if you're looking, you see all chloride salts are aqueous. And then there's the word unless any of these are true. Zinc is not silver, zinc is not mercury, zinc is not iron. So it must be aqueous, okay, based on the rules, okay? So now that we have our reaction made, and this is why I said, I know we're going a little slower, but hopefully if you were struggling on little parts, you're seeing every little part of it now. We're not going fast. We're reviewing a lot of stuff from last semester, okay? So now that we know how to build our formulas, how we told it was single replacement, how to predict our products, and now we see our products, what do we have to do now to this reaction?
We have to balance the reaction.
We have to balance it. So I'm going to call on someone else to balance it. You did a great job. So everyone try to balance it, and you can drop in the chat in a direct message. You can DM me the coefficients when you're done. But Adhish, you are going to tell me out loud when you are done what you think they are. Yes. I see a lot of direct messages. Still waiting for Adhesh to pop up. Are you here? Yes, you are here. Let me know when you're ready, bub. See, a lot of them are right. This one, try again. Yes, I see lots of things that look good. Okay, Adhesh, did you drop it in the chat or did you say it out loud? I'm so sorry, I'm having a hard time.
I can say it out loud.
Awesome, yeah, because I got about 100, like I get a ton of them really fast, so I was trying to look, but if you could tell me out loud, what did you end up getting?
I got 3, 2, 2, 3.
Okay, so, and that works perfect because chlorine is the one that is weird because there's 2 chlorines on the right and 3 on the left. So that means we have to multiply to make them 6. So we need 2 of these for sure and 3 of those. Since there's 2 irons, I put a 2 in front of the element. Since there's 3 zincs, I put a 3 in front of the element. And now we are perfectly balanced. Awesome. So now we are at the point of what we did for the Google Slides activity. So I know we spent a lot of time reviewing, but this part is the part every time I've had someone come to tutoring for QC 7.1. And when I was going through all of the answers, because I went through your last attempt and gave you guys points back and all of that, I sent you an email. This was the part that you guys messed up, like in the numbers wise. So I just wanted to make sure we did this really solid. Okay. Now, next up. Magana, what do I do now? I have my balanced reaction. What do I do now?
You have to start the railroad tracks.
I have to start the railroad track. So what do I put first in the railroad track?
6.521 grams of zinc.
Yep, so this 6.521 is the only number I'm given. So that's what has to start my railroad. So 6.521. And I love that you said grams and zinc. You fully dressed your number and you want to dress every number in your equation. That's wonderful. Okay. Okay, that's what I'll need. All right. So now that I have that number, what do I do first? What's step 1?
You have to figure out how many grams of zinc are in 1 mole because you have to convert to moles first.
Yeah, step 1 is convert to moles, right? And we're going to do that right here. This is step 1. So you need to figure out how many grams of zinc are in a mole. How do you do that?
You go to the reference packet in the periodic table and you have to see like the mass of it.
Okay, so when you did that, what did you get for zinc?
I got 65.39.
60.5.39 grams of zinc for every 1 mole of zinc. And why did you say to put that on the bottom?
Because you have to cancel out the units.
Yes, if we cancel the units, this is how we check our work. We don't want grams of zinc anymore, so they need to be on opposite sides. We now have moles of zinc. Awesome. Gonna pick on the next person. Corey, give me step 2. What do I do next?
Do you have to set up the mole ratio?
Yes, so step 2 is mole ratio. Okay, and how do I decide what I need to compare?
You take your given, like, I guess, a molecule or whatever, and you put it under the unknown molecule or the thing that you're going to. So it would be like zinc on the bottom and iron on the top.
Yes, so we have zinc, so we use this number. So we have 3 moles of zinc on the bottom because we're trying to cancel out these, which is what you said, which is lovely. And then we're going to iron because we know our question is mass of iron. We identified that in the beginning. I should probably erase that line through it. We're going to mass of iron, so we need to go to iron. So that is the 2 moles of Fe. Awesome. And then last person for the setup. What is the last step? Lucas, what do I do now?
So you do so we have to find the mass of iron.
Yes. Why do we need to find a mass of iron? What's that third step if you had to generalize it?
We have to convert it to grams.
Yeah, convert to what's asked, right? And in this case, they asked for grams of Fe, which we identified in the beginning, right? So we have moles of Fe. How do you convert that to grams? Tell me how you did that.
You need to do moles on the bottom.
Okay.
And then the mass of 1 mole at the top, but let me pull that up.
Yep, and remember guys, that's on the bottom of the box of the periodic table. This is step 3. This is step 2.
Sorry, my internet's really bad. It's
Mine
loading
too.
right now.
You're totally good. Mine is really bad as well.
Is it 55.85?
So it, yeah, 55.85 grams of iron per 1 mole. Awesome. So next up, Jessica. Jessica, what do I do now? I know I'm in grams of iron, which is what I wanted, right? What do I do now?
You put like brackets on every fraction, then you type it exactly like that into a calculator.
Exactly. I love the way you described that. So I would type open 6.521 close, open 1 over 65.39 close, open 2 over 3 closed, open 55.85 over 1 closed. When you did that, what did you get out of the calculator?
I got 3.713.
Well, give me everything out of the calculator the way you got it.
Oh, 3.71308.406.
Okay, so we're gonna stop there. So you only gave me 4 numbers. Why did you do that?
Because of significant figures.
Yes, because of significant figures. So if we go back, I've used all the colors already. If we go back here, we see there's 4 sig figs that we are given. So we have to keep 4 sig figs here. So we start with the first non-zero number, count 1, 2, 3, 4, draw the line, round back. 4 means that this stays to be a 3. So I get 3.713. What else do I need to include on my answer?
Your units and like the iron.
Yes, the grams of iron, and this is done. If you are on a lab or something that you're writing me the answers, that's not like a numerical check thing on Quick Check. If you're physically writing things and you do not put the unit and the element, I'm going to assume it's unicorns. And unicorns is not the correct answer, and therefore I will mark it wrong. Okay, so if you don't tell me, I'm assuming unicorns because that's what I want to do. So make sure you put the actual thing. Okay, put the actual thing on the problem. All right. Yes, you should use the whole molar mass on the periodic table instead of rounding. We don't round until the end. A very good example of why. Okay, so I'm going to do this right down here. If you add 25 plus 25, you get 50. And if I ask you to round that to 1 sig fig, you still get 50. But if you said, oh, I need 1 sig fig, I'm going to round everything to 1 sig fig. These would have became 30. And now you have 60. So your answer is 10 off because you rounded in the middle, right? You rounded to 1 sig fig in the middle and kept at the end. This is not good, okay? This is not good, not good. So don't round until the very end, all right? Just, it turns everything off, okay? There's a whole study about how like not doing sig figs correctly made the space mission take longer because they went to the moon with less technology than it's in your calculator. So all of that was done by hand and they had one person rounding wrong and they had to redo a bunch of calculations and it was crazy and weird and whatever. But sig figs are important, guys. Sig figs are important. That's all. That's the moral of the story. All right. Any questions on this before we move on? I know we spent a lot of time on it, but there's a reason because we have had a lot of people struggling with this. Every year we have a lot of people struggle with this. So I want to make sure you're really solid. Okay. I used whatever was typed. So see, I used whatever he told me or whatever, which is fine that he said 8.5 or whatever. He maybe looked it up on a different periodic table. Always use the periodic table in the reference packet because everybody rounds different. But I was just using the values that someone was saying to me. That's why. There's no good reason. And it's not your fault either. For the purposes of this problem, demonstrating the process, I'm not whatever, but it's okay. All right. Any other questions? All right, fabuloso, it's Kahoot time. Kahoot time. Dun, 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 dun. Play, teach. And this is the part of the class where if you do not have your Unit 7 notes in front of you, you will not do well. You also need your reference pack in front of you, or you will not do well. All righty. I'm gonna wait for you guys to join. I'm gonna reset my wheel here. The internet's slow. There we go. Took forever to load. All right, I need 38 people joined. So if you don't see your friend, text them and be like, what the hey? All right, we are joining. So 39 people joining. Woo woo. Still waiting. Make sure you have your reference packet and your notes in front of you. We're going over electrolytes and solubility, so you want that electrolyte section open in front of you. We already did the stoichiometry section. I have a couple more people that need to join, giving you just a second. Okay, I'm gonna start. All right. Well, I see the chat just dinged. Yeah, you're good, Kira. I saw it. I just didn't get a chance to respond. All right. What is an electrolyte? What is an electrolyte? This definition is true all the time, not some of the time. All right. An electrolyte is a substance that conducts an electric current when it's dissolved in water. Okay. There are electrolytes that conduct poorly. There are that conduct well. But to be an electrolyte, the only requirement is that it conducts electricity. So the red answer isn't always true. Okay. Compound that conducts an electric current when dissolved in water. All right, next up. What is a non-electrolyte? Good. And if an electrolyte conducts electricity when dissolved in water, a non-electrolyte does not conduct electricity when in water. Those are absolutes. Electrolytes conduct when dissolved. Non-electrolytes do not conduct when dissolved. End of story, period, exclamation point. All right. What is a weak electrolyte? What is a weak electrolyte? All right, blue and green, good job, guys. So a solution that conducts electricity poorly does so because the compound does not dissociate completely into its ions. It only dissociates some of them. We'll talk about why in a little bit, but just know sometimes compounds only dissolve slightly or partially, therefore it does not conduct electricity as well. Other compounds dissolve completely, as in everything goes from a molecule to an ion. So there are more ions present and it conducts it well. Less ion presence conducts it less. So a solution that conducts electricity poorly because the solute, which means dissolved thing, does not dissociate into ions completely. Okay, so blue and green were both true. Good job, guys. And no one can catch Ganesh, apparently, who likes mayonnaise. All right. A dissolved substance is an electrolyte when it does what? I didn't hear what you said, Ganesh. Or Gus, whatever you want to be called right now. Mayonnaise. Good. We just talked about this. It has to dissociate into ions. Atoms is not true because those are uncharged particles. And for electricity, which is a flow of electrons, to be able to move, it has to be able to bounce from positive to negative charges to create movement and flow. Okay. Dissociating into protons would be a nuclear reaction where we split a proton off of the atom, which would be fission, which would explode. And that nothing explodes every single time you dissolve it in water. It's not a thing, right? It explodes for that reason. There's no radiation. And then dissociates into electrons. We are not dissociating electrons in beta emission. The electrons have already transferred. These are ionic compounds that are held through electrical attraction, and those electrical attractions break up for a very specific reason we will discuss later, okay? But ions are still who they are, just like couples and people. You're still who you are, you're just not together anymore, okay? It's the same thing, they just break up. That's literally it, okay? The ions stay what they are, but they break up. Carter, you're doing great, man. All right. When a compound doesn't dissociate into ions, this makes it a what? Good, it makes it a non-electrolyte. If it is an electrolyte, it conducts electricity because it dissociates into ions. If it is not electrolyte, it doesn't dissociate into ions or doesn't dissociate at all. So that would be a non-electrolyte. Oof, I'm not, I was gonna need water. When ionic compounds dissolve in water, they what? I'll answer that question in just a second, Darshan. Hold on. Yes, they conduct electricity because they are electrolytes. So ionic compounds are electrolytes. Not ionic compounds are not electrolytes, period. Okay, so I got a really good question in the chat. Is dissociation and decomposition the same? Like, is it a chemical reaction? Dissociation is not a chemical reaction because no electrons are exchanged, no bonds are broken or formed. Sodium and chloride exist in the exact same state they did before. They are just being pulled apart by the water. So it's not considered, like, dissolving is not a chemical reaction. We actually call it a dissociation equation, not a chemical equation, because it is not a reaction. It is a physical change, not a chemical one. Because if you evaporate the water off, right, those sodium and chlorides reform that solid crystal. Same thing like when you leave your soup bowl out or whatever, and then the water dissolves and you have those little crystals stuck to the bottom of the glass because you left it out too long. That's just the salt reforming after the water evaporates off. Okay, so it is not a chemical change. It is not a chemical equation. It is a physical change, and it's called dissociation because they are just merely moving apart, and they will move back together once the barrier is gone. They're not going to form a new substance. Nothing new is formed. Does that make sense? Okay. All right. That was a very good question. Very, very good question. Okay. Dissociation equations was the next question, right? So how would we write the dissociation equation? I didn't even pay him to ask that question, by the way. Like, that was awesome. Yes. Okay. So let's talk through why these other ones are not right. So to be a dissociation equation, the only thing that's changing is its phase state and it's separated. So you have to include what it is and its phase state. This is not true because it's an ionic compound made of ions, not atoms. These are atoms added together. This would mean that the electron configuration changed and it has not. So sodium and chlorine must be ions, not atoms. So this can't be it. This one has the phase state, but not the charge, meaning an aqueous atom. That is not a thing, right? So this has to have the charge and the phase state. This one has the charge, but not the phase state. To be a dissociation equation, we are identifying when it's solid and when it's aqueous, okay? So you have to have the charge and the phase state, which is why the yellow one was correct, okay? All right, and we'll practice writing those in just a minute. Acetic acid, this is where you need your notes. Is it a strong electrolyte, a weak electrolyte, or a non-electrolyte? All right, weak electrolyte, weak electrolyte. Does anybody know why? Or do we make really good guesses? Yes, Sangeet, why don't you tell everybody, not just me? You did great. You've been confirmed.
Because it's a weak acid, so weak acids and bases are weak electrolytes.
Yes, so strong acids are strong electrolytes. Strong bases are strong electrolytes. Weak acids, weak electrolytes. Weak bases, weak electrolytes. This is because the definition of a strong acid is one that dissociates completely. So like a hydrochloric acid or hydrobromic acid, every hydrogen turns into H plus, every bromine goes to Br minus, every single one. A weak acid is when we add it to water and sometimes it doesn't break up. Sometimes it breaks up and sometimes it doesn't. It's a incomplete dissociation. And there's a value called pKa. You'll talk about AP and IB if you come, but it's a weak dissociation, weak acid, because not every ion is formed. Less ions in solution, less electricity conducted. That is why, okay? So if you need to know if an acid or a base is a strong or weak electrolyte, you have to refer to your notes. If you come to AP or IB, you'll have to have these memorized, but you don't yet. You can use your notes. We have open book tests. So like highlight this, circle it, bend the corner of the page, put a Post-it note. You will need this for your test and for your QCs. Okay, this right here, this part that I'm showing you. It's very important, very, very important. Make a note, okay? So weak acid, weak electrolyte, okay? Ionic compounds that are not acids or bases are just, they dissociate completely. You don't have to worry about it. It's just the acids and bases that are weird, okay? All right. Bob, you're killing it, dude. Get it. We're almost halfway there. Sucrose or table sugar, what you buy in a bag at the store that gets everywhere. Good. It is a non-electrolyte. So since a lot of people were split on this, we're going to talk about it for a second. Why is this not an electrolyte? Does anybody have a clue? I'll open it up to the floor.
It's not included in the strong, oh, it's not a strong acid or strong base, I don't think.
Right, but it's so table sugar isn't an acid or a base, period. Like Like, let's talk about like real talk. Like it doesn't have an H in front. There's no OH in the back. So we're not looking at acid and base table here. What are we deciding? Yes, Milan, you said it to me, say it to everybody. Yes, yes, yes. Yes.
Is it because it's covalent?
It's covalent. It doesn't form ions, guys. Does not form ions. It's not an ionic compound. Covalent compounds are not electrolytes, okay? Table sugar is covalent. It dissolves because it's polar covalent, but just because it dissolves does not mean it conducts electricity. It has to dissociate into ions. This dissociates into atoms. Scale of 1 to 10. Scale of 1 to 10. Don't get confused. Okay, we're getting there. I'm getting there. I appreciate the honest answers. We still have more to go. And if you haven't watched your notes, watching them now will make a lot more sense. And please watch your notes. It is an expectation. Hydrochloric acid. Is this a strong electrolyte, a weak electrolyte, a non-electrolyte? Okay, it is a strong electrolyte. How did you know? Hydrochloric acid is right here. It is a strong acid, so it is a strong electrolyte. Use your notes. Use your notes, use your notes, use your notes. Use your notes, use your notes. Use your notes. Okay, all right. Magnesium hydroxide. What do you think? It is a weak electrolyte, and a lot of us got this wrong. So I'm going to go back to the wheel and we're going to ask some things. All right. So magnesium hydroxide. Victoria, what do I need to think about when I see hydroxide? What should that tell me? Are you here, Victoria? Victoria.
I actually do not know. I don't really understand it as like the concept of it as much.
Okay, so what we're deciding is whether something dissociates into ions all the way, as in every single molecule will dissociate and separate and break up. Will some of them break up, but others not break up? Or will they either not break up at all, as in they're not soluble, or do they break up into atoms, as in covalent, instead of ions? Do you understand what the question is asking you?
Yes.
Okay, awesome. So now it's saying, is magnesium hydroxide, when you add it to water, dissociating completely, dissociating partially, or not dissociating or dissociating into the wrong things? Okay, so we need to figure out what magnesium hydroxide is. So magnesium, is that a metal or a non-metal?
It's a metal.
And then hydroxide is a polyatomic ion made up of what type? Metal or non-metal?
Non-metal.
So we have a metal and a non-metal. What type of compound is that?
Is it ionic?
It is ionic. So if it's an ionic compound, we know it's some version of electrolyte. It's not going to be a non-electrolyte. Okay, because ionic compounds dissolving make electrolytes. That part makes sense.
Yes.
Okay, so now we have to decide if it's an ionic compound that is not an acid or a base, it'll dissociate completely. So if we know if this is an acid or a base, we have to know that first. So is this an acid?
No.
No, because it doesn't have the word acid in it, right? Acids kind of call themselves out. Is it a base?
No.
So how do you tell a base? Do you remember? Okay, so the silly way to remember that's slightly inappropriate, but you guys are teenagers and I'm sure you've heard worse, is that like magnesium hydroxide, hydroxide's always in the back. And hydroxides are all about the base, like the song, because we know she's talking about butts. So you look at the butt of the molecule, and if the butt is hydroxide, it's all about the base. Okay, and those are bases. So if you have hydroxide in the back, it's a base. So this is a base. So once we determined if it's an acid or a base, we know it's a base. Where do we go look?
Solubility.
Not the solubility part, because we know acids and bases are soluble, but where in our notes do we look? What do we have to determine? We know it's some version of electrolyte. But if we look here, we have, if we determine that that base or that hydroxide is a strong base, it will be a strong electrolyte because it means it breaks up completely. If it is a weak base, it'll be a weak electrolyte because by definition, weak bases do not dissociate completely. Does that make sense?
Mm-hmm.
So is magnesium hydroxide a strong or a weak base?
Weak.
It's weak because it says hydroxides with a metal from group 1 or group 2. And magnesium is a group 2 metal, but it is one of the exceptions. So it is a strong base unless it's based on beryllium or magnesium. And this is a magnesium hydroxide, so it's a weak base and therefore a weak electrolyte. Scale of 1 to 10 now. Does that make more sense now that I went through the whole process?
Yes, thank you.
Always, that's my job. Thank you for validating my employment, getting me paid. Okay. Awesome sauce. I see those numbers going up and that's the best direction. Okay. All right, CO2. Strong, weak, or non-electrolyte? All right, is a non-electrolyte. You tell me why.
It's covalent.
It's covalent. Covalents dissociate into atoms, not electrons. And technically CO2 can be contained within a liquid, right? Anytime you drink a carbonated beverage, your soda of choice, your sparkling water of choice, anything bubbly, it's CO2 gas dissolved in water. And that's why cold has more bubbles because cold liquid is denser than warm liquid and therefore holds the gas better, right? We'll talk about that during gas laws, just preview. It's super fun. But it's a covalent compound, so it is not ionic and therefore not an electrolyte, okay? All right. Calcium hydroxide. Is this a strong electrolyte, a weak electrolyte, or a non-electrolyte? All right, Esty, tell me why.
I was a bit confused on this one.
So let's walk it through. I see hydroxide in the back. So what kind of compound do I know that is?
Wait.
Hydroxides are all about the
hydrogen.
So remember the song? It's a really bad song. All about the. You know that song? Is it already too old? Am I already too old? Is the song already?
No, I know it. Wait.
I was like, don't make me feel that old. Oh my God, I thought that was more your age than mine. Yes, all about the base, right? Hydroxides are all about the base, no acids, right? And that was a song we used to sing in person. It was awful, but it was amazing. So hydroxides are all about the base. So this is a base. So how do we determine if it's strong or weak? Where do we go look?
The periodic table?
You will need the periodic table, but if you go to your notes, did you find this page in your notes? Did you find this section? I can zoom out a little bit. Okay, this section, okay? So we're gonna zoom in. If it's a strong base, it's a strong electrolyte. If it's a weak base, it's a weak electrolyte. So we know we have calcium hydroxide. Wow, stop. Okay, we know we have calcium hydroxide. So where is calcium on the periodic table?
Let me check.
Sounds like a plan. You go check. No rush.
It's in group 2 with
So we
the
see OH with any group 1 or group 2 metal, unless it's beryllium or magnesium. Calcium is not in the exceptions. So is this a strong base or a weak base?
it's a strong base,
So therefore it's a,
strong electrolyte.
does that help?
Yes.
Awesome. Good stuff. All right. Iron 3 sulfate. Okay. Samir, tell me why.
It's because iron conducts electricity well.
Well, iron is a metal, but we're not talking about metal iron. We're talking about aqueous iron. So it's a little different. It's an iron ion, not the iron element. Okay. So do you have any other thoughts that are related? I'm sure you have other thoughts, but any other thoughts related to iron 3 sulfate?
I'm not sure.
Okay. So let's break it down. What type of compound is it? Covalent, ionic?
It is ionic.
Yes, because it is a metal and a non-metal. Sulfate is a non-metal polyatomic ion, right? So we have a metal and a non-metal. So we have an ionic compound. So is it going to be an electrolyte or not an electrolyte?
It's going to be an electrolyte.
Yes, because ionic compounds dissolve into electrolytes. Next question, is this an acid?
No.
Is it a base?
No.
So any ionic compound that's not an acid or a base is a strong electrolyte. Does that make sense?
Yeah.
Yeah, because the acidic and basic qualities are why they don't dissociate completely half the time. It's really complicated, and we'll do that during the acid-base unit that's coming up next. That's unit 8. So excited. It's going to be great. You're going to love it. Okay, but iron 3 sulfate is an ionic compound that's not an acid or a base. All right, shifting gears. Is this soluble or insoluble? Pull out those reference packets. All right, it is soluble. So let's take a look at that solubility chart. Okay, so this is bismuth nitrate. So the rule that applied was, come here, pen. Okay, I've grabbed the wrong pen. Is this nitrate right here? All nitrate salts, because we had BiNO3, with no exceptions, are soluble. So that's how we knew it was soluble. Okay. All right. Next up, sodium phosphide. Make sure you have your solubility chart out. Oh, sorry. Hold on. All right, it is soluble, okay? Sodium phosphide. Sodium is a group 1 metal, so it's considered in a compound a group 1 salt. So all group 1 salts without exception are aqueous. So this one had to be soluble or aqueous, okay? All right. Next up. Okay, they are soluble. They are soluble. If you go back to our sheet, okay, I erase some of this because it looks ridiculous. Okay, we see ClO4 is on the third rule. So ClO4 without exception is aqueous. Wow, that highlighted everything. I did not mean to do that. That's okay. All right, next up. Boron hydroxide. Boron hydroxide. Yes, it is insoluble. If you go back to our rules, all salts of hydroxide are insoluble unless it is group 1. Boron is group 3. Ammonium, barium, strontium, or calcium. Boron is none of those, so it must be insoluble or solid. 2 more questions. Zinc phosphate. All right, it is insoluble. It's one of those magical rules. Zinc and phosphate, neither of them are on the table. Zinc is not up here, phosphate is not up here, so it falls under this rule. Everything else is insoluble. Okay, that's where we're at. All right, and last question. Calcium hydroxide. Calcium hydroxide. All right, so we have soluble because in our compound sheet, we have all salts. Why did it do that? Stop. We have all salts of OH minus, but one of the exceptions is calcium here. So calcium hydroxide is aqueous because it's in the exceptions. Awesome. All right, guys, I'll see you one. And then we'll do one last thing real quick. I know I told you guys it'll be a little longer today, but that's okay. You asked really good questions and we dug really deep and I hope it makes a lot of sense. All right, Maddie, good job. Woo, round of applause for Maddie. Yay. Okay, so Maddie, if you ever come on campus, come get your sticker. All righty. So next up, and this is the last thing, is we're gonna go next level with particulate diagrams. So I'm gonna show you how to do one and you're gonna do the rest. So these particle diagrams are during dissolution or while they're dissolving. And this is gonna explain why atom or ions break up in water. Why does the water make them break up, right? It's the only thing that's different. So why do they break up? So before we add it to water, like picture like potassium fluoride, like it's table salt, because it's a similar idea, right? A group 1 plus a group 17. So Sonali, what phase is potassium fluoride before I put it in water?
Is it a solid?
It is a solid. Ionic compounds form crystalline solids before they're placed in water. Awesome. So it looks kind of like table salt, but not really. Kiera, after I dissociate, after I put them in water, what do I look like? What do I form?
Would it be potassium and then with a plus charge?
Yep, because
and that's aqueous.
Yes.
Plus fluorine with a negative charge, aqueous.
Yes, and that is because remember when we drew these LDSs, sodium had no electrons with a positive, and fluorine had all the electrons. It's not letting me draw dots, but just pretend that's 8 dots with the negative. So this is what it actually is. That's what this means. And all that happened is we broke them up. That's literally it. That's why the charges exist there. So I'm going to erase those so it's not in the way. All right. So this is a dissociation equation. It should also be balanced because dissociation happens in proportions, right? So this is a 1-to-1 ratio. So we have 1-to-1 for our ions. Awesome. So when you're drawing this, you can just draw the ion. LDS, I copied and pasted poorly, including the positive and negative charges. So just ignore that. I shouldn't have kept that. That was me not copying and pasting well from last class, okay? So draw the ion for each dissociated ion, including positive and negative charges. Now you need to draw 3 water molecules surrounding it. So based on what we learned about water last time, which part of the water molecule is going to like potassium? Minahil, which one? Are you here? Are you here? Are you here? No? Okay. Renee, which part of the water is going to be attracted to potassium ions?
The oxygen.
Oh, that's okay, Manahal. I appreciate you trying to unmute. I don't know why. Yes. Oxygen is going to be attracted. So when I draw my 3 water molecules, I'm going to draw them where oxygen is attracted, right? Because each oxygen is partially negative, right? And the potassiums are positive, so they are attracted to one another, okay? This is an attraction, not a bond. Okay, so this is where we're going to pause. Actually, no, I should finish and then we'll pause. Okay, for fluorine, which part is going to be attracted to fluorine? Dun, 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 dun. Jonavi, which part's going to be attracted to fluorine?
The hydrogen, because it's plus.
Yeah, the hydrogens are partially positive. So I'm just going to put partial positive there for one of them because it takes forever to draw these. Okay, so if you ever have to draw a particle diagram or select one, that's what you're looking for. Ion with a charge with the correct opposite charge surrounding it, okay? So really, really weird. Does anyone want to go down a really weird question hole with me? I was going to use a random question, but it's a really weird question. It's going to demonstrate a point though. Anyone up for some weirdness? Yes, no, maybe so. All right, Audrey, are you here, Audrey?
Yeah.
Awesome. I'm gonna ask you a question. If I told you to brace yourself and my 6-year-old tried to push you over or pull you away, would she be able to?
Probably not.
Probably not. A single tiny human doesn't have a lot of strength. So my single tiny human is like the attraction between oxygen and potassium. So right now, potassium and fluorine are very strongly attracted together through one electrical attraction. This attraction with oxygen is weaker, but it exists, okay? Now, let's clone my daughter 100 times, and then she tries to push you over or pull on you. Is she gonna win?
Yeah.
Yeah, 100 toddlers is a lot of toddlers, but a lot of little things make up to be a bigger thing. So the sum of the whole is greater than the sum of its parts, right? So when you look at like something like a rope is very thin, but it's made up of a ton of different strands woven together, which makes them stronger versus just having a solid like leather belt. I wouldn't rappel with a leather belt. I would rappel with a rope because it has more things acting together and they create a very strong force. So it's all of the oxygens. It's not just one oxygen. This is 3-dimensional. So 3-dimensionally, oxygen is surrounding potassium like a bubble and pulling on it together. And that's what moves it away from fluorine. And at the same time, fluorine has a pocket of hydrogens around it, right? It's inside a little bubble of hydrogens, and they're all pulling on it together. So they're both being pulled apart by hundreds of thousands of millions of things, right? Like really, if you had a mole of water, a mole of things, which is infinite. Like you would have to have as many years as the earth has been alive in seconds, like all 4 billion years in seconds again, before you even got to a mole of seconds. Like a mole is a lot. So all of those things are pulling on it at the same time. So it's very strong, and that's why they dissociate. Does that make sense? So it's a bunch of little forces working together instead of one stronger force. So yes, the bond between potassium and fluorine is stronger than the attraction of oxygen, but thousands of millions of attractions of oxygen are what pull it off. Okay? And that's why they dissolve. Guys, try calcium chloride and then we're done for the day. Try calcium chloride. Physically try it, because you have to be able to do this for your exams and your QCs. I want to make sure you got it. All right. Let's see, dissociation equation, give it to me. Let's see. Eden, give me the dissociation equation at the top.
Would it be, well, first, is it a solid?
Yes, it is always a solid to start. And then what happens?
So then, Cl would be positive and then aqueous.
Yeah, Ca is positive.
Ca.
Yep, 2 positive and aqueous, good. And then what else?
And then Cl would be negative and also aqueous.
Okay, so right now this is CaCl. So we crossed off Ca and we crossed off 1 Cl. So is it balanced yet?
Oh no.
How many chloride ions dissociate for every calcium?
1 or 2.
2. So this needs to be 2 Cl minuses. So when you drew your diagram, you should have Ca2 plus, Cl minus, Cl minus. Okay. So the positive one, let's see, what part of the water would be attracted to calcium? Izzy.
Would it be oxygen?
Yes, the oxygen is attracted to calcium. So you would have drawn your 3 water molecules with oxygen stuck to it. And then the opposite is true for these, right? I'm just going to do it for 1 chlorine because it takes forever to draw and I'm being lazy. That's okay. Okay, there we go. So we have a pocket of hydrogens. So the last thing to show you was a question I got last class, and I pulled this up because it was a really good question. Someone's like, well, why isn't it that the oxygen and the hydrogens are dissociating on the water? And it's because water is a polar molecule. They're very attracted to each other as well. So it's cohesion and adhesion that you learned about in biology. So if this is a solid piece of salt, the water molecules on the surface are kind of starting to surround them and pull them away. So if you track one of these, you'll see all, like this guy, he keeps getting pulled away and eventually would get pulled away all the time. That's why when you just put salt in a jar, it takes a long time to dissolve because these water molecules don't have access to the internal salt molecules. But when you stir it, now every water is interacting with every salt and it dissociates a lot quicker because those waters surround the salt particles and pull them apart. Like you see this guy pulled apart. See how all these negative oxygens, like pick this one positive ion. All the oxygens are kind of like pulling on it and tag teaming away from this guy. They kind of surround it. So this is what it more looks like on the actual level. And that's not fully dissociated. But yeah, so that's kind of what I'm talking about. So that is all I had today. Okay, that's it. I know it was a lot more and we spent a little more time on stuff, but hopefully it's very clear. Tutoring today after school if you need it. Tutoring tomorrow morning before school if you need it. You need to come to one of those if you told me you needed an extension. Otherwise, your extension will not be granted. And I think that's it. All right, guys. If you have any questions, you could stay on, but otherwise, have a good day.
Thank you, you too.
Bye, guys.
Thank you.
So the QCs for these topics, they're due Tuesday?
Tuesday. So you have the weekend to do them.
Okay, thank you. Have a good day.
You too.
Thanks, Aslangli. Have a good day.
You too. Bye. All right, do you guys have questions?
Yeah, for the QC 7.1.
Okay, so yeah, I went through them all. So was that on the last attempt or attempt before the last attempt?
It was one before the last.
Okay,
I mean, I didn't take my last yet.
No, okay, well, so I looked through just the last attempt. So if it was like a prior attempt, I might not have seen it. I'll go look at yours. I thought I caught them all, but I'll go look. So let me pull it up right now to make sure I'm looking at the right thing. So grades, 6th period. Okay. And let me go to speed grader for you. Yeah, actually mine is showing that you haven't even submitted 7.1.
Oh, but I took 2 attempts and
I believe you. I believe you 100%. It's not the first time this has happened today. Let me show you so that way you know I'm not. So if I pull up you and I pull up your grades, it says it's missing.
yeah, on my canvas, I think I saw the same thing, but
Yeah, so this is why I'm like, you can still see my screen, right?
yeah.
Like it's not that you didn't, I didn't send me a screenshot and I would be more than happy to fix it for you.
Okay, thank you.
Awesome, no problem.